please. You're welcome.
You can start.
Yes, please.
Can I start now? Oh,
Yes, please begin.
okay. First, preliminaries. A lot of physical model is describe such a situation when corresponding equation has a very strict form. It is something like KdV equation with constant coefficient and assumed to describe non-dissipative medium. But from the point of view of mathematical physics, to think that such models are realistic is not true, because the media, ambient media where the processes develop, vary in its characteristics both in time and in space. And this leads to the coefficients which are not constant. And sometimes it is necessary to add some terms into the equation, such as dissipative terms or something like that. KdV equation has a lot, an infinite number of interconnected conservation laws and infinite number of symmetries, but any such addition ruin this castle of structures. But what to do in the real world? In fact, such such effects as non-constant coefficients and additive terms are very interesting from the real point of view mathematical physics, and therefore it is very interesting whether such perturbed equation inherits or retains some properties of the initial ideal equation, such as KdV. The famous example is KdV equation, infinitely many conservation laws and symmetries, and KdVB, Burger's equation with additional term and only one conservation law. But these conservation laws, which are intrinsic for KdV equation, are in some use of investigating the development of KdV Burger's equation, and the question of what is inherited in perturbed equation is very actual and very interesting question. Later I will mention some lively field in this direction, but now let's return to basics. If the system of equation, ideal state, is perturbed, then its conserved quantities or conservation laws are not after that in fact conserved, but their rate of decay can be readily described. Now let's go for another slide. If something added, then the quantity is no more constant, and its velocity of decay is called the decay rate. And this decay rate is very, very useful in qualitative research of equation of perturbed equation. If we see for perturbation with some additional term, such as KdVB equation, then for system, the additional term for a system we assume to be of a rather simple form. It's additional term and in every equation, and if diagonal matrix is 0, then we get the initial equation. Then in this case, the decay rate describes by the simple formula. It is a scalar product of additional term and so-called generation function of conserved quantity. It is a very simple fact, and it was proved by me a lot of time ago. Some remarks about this formula. The velocity rate is described by the right-hand side, but this right-hand side, because this delimiters are in fact means integration, this additional this right-hand side, of course, is not unique, because you can change it for integrating bar parts or adding some full derivatives and so on. But it may be so that the right-hand side is simply null, or it may be in effect an exact form. Then you can see that this conserved quantity still retains the 0 right-hand side, and still it is a conserved quantity in spite of this additional term in an equation. In fact, this may be put in a more transparent form. The right-hand side, the scalar product of generating function and additional term must be in an image of operator D. And of course, the intersection of principal ideal, that is the right-hand side of this inclusion, with image of the operator is huge. In fact, that means that there are a lot of additional terms which retain in perturbed equation, retain their a certain conserved quality. The conserved quality as a norm, decay, that is the velocity of decay is not zero. But this decay rate are individual for any quantity, and they may differ significantly. The first method used in this direction was invented by Taylor when he was studying the quasi-stationary state of plasma in tokamak. And the simple phenomenon, the physical phenomenon which described by this quasi-stationary state was approximately as such. The energy was declining, but some other conserved quantities retained were in fact for a time constant, and this means that was quasi-stationary state from the point of view of research. Precisely when energy was monotonically declining and momentum was constant, there was an interesting states of plasma which were for short periods were quite stable. The procedure was known is known as a Taylor trick. It's rather simple. When we consider the Euler-Lagrange equation where energy is minimized and momentum is presumed constant, the system added to initial system on plasma gave such solutions, at least they were very close to the real solution. This Taylor trick is widely used. There is a school in Moscow University, there is a school in Holland where this trick is used to obtain not quite exact solution, but they are quasi-stable. This is very important for numerical methods. Selective decay with selective speeds of different conserved quantities is a instrument to obtain first approximation which gives stable result, which is not very easy to obtain for systems with many spatial coordinates and many equations in it. There is a recent paper in which these new developments are described. There are other applications for this selective decay. I mentioned that coefficients in equations, for instance, in KdV equations, are not necessarily constant. It is my previous work. Soliton KdV has used in a layered piecewise media, piecewise in connection with dissipation and dispersive characteristic of the media. And it is not easy to, give a general answer. One of the KdV properties is that the transition signal when he use the previous media and comes into the another, it will this signal will scatter or split in a number of solitons. It is not very easy to use to obtain the number of the solitons or their amplitude or velocity, but using the inverse scattering method, but using the selective decay, it is not quite. It is very simple procedure to predict this resulting solitons, the resultant scattering of soliton. This is the case when coefficients of the equation becomes non-constant, and the selective decay may predict where is the change, where the change go into the simple solutions of KdV with solitons, for instance. Another application, also my work, was applied to in the case when Taylor trick is implemented to some well-known equation, KdV Purgis, BBM, and two-dimensional generalized shallow water. The extremals of Taylor trick, the solutions of this equation are in fact associated with first order PDEs and traveling wave solutions of all the initial equations. In this talk, I will demonstrate what will become of algebraic structure of ideal state equation if they are added with some terms which retain a specific conservation law. Results are interesting. You will see it below. They are demonstrated on KDV, indispensable, and with some equation in three two equations in 3D space. Well, begin with simple examples. The KDV equation is first two terms is KDV, and plus dissipative term, it is KDV-Burgers equation. For KDV, first three conservation law are conserved quantities, in fact, are as follows. And its their generating function are given in the following slide. Recall that this is conservation law for KDV, that is for lambda equals 0. But this quantity is conserved and in KDVB too, because the right-hand side is the full derivative. But the other two, momentum and energy, are not conserved anymore. It's simply to obtain its decay rate, and momentum declines monotonically. This is decay rate of momentum. It is equal to negative result, and the energy decay rate is like that. Energy does not necessarily decline with this addition of with the addition of dissipation. We want to obtain perturbation which retain momentum. I return back and remind that this right-hand side must be the full derivative. That means that this is generating function of momentum, and this is additional member in perturbed equation. It must be the full derivative of something. Well, of course, the orders or in derivatives are such that I want so to obtain small, not huge answers. Here is total derivative of full differentiation with respect to x. It is easy to see that right-hand side must be divisible by u. Generally, of course, these functions, whether it is f or a, are general functions, but in mathematical physics, it is wise to consider only functions which are differential polynomials in u and its derivatives. Therefore, right-hand side is divisible by u. That means that a is u square multiplied by some other function b. Then that is previously was a, and we get another simple, very simple result. And so we obtain that it is u by f, and by, when u is omitted, we obtain that the answer which can be, which are the perturbation which retain momentum. For the second order, one may see that f is linear by by xx. B is quite arbitrary. Let's take B as u by x. Then perturbed equation is has this form, and momentum is still its conserved quantity. Of course, this construction, which is very simple, may be generalized, and if g is the generating function for some conserved quantity, then one special dimension, then f given by this formula is the addendum to initial equation, which retains that conserved quantity. When where phi is quite arbitrary. This equation has traveling wave solutions. Here they are. If we want a solution which has some physical, we move to the left, and if we want some physical meaning of solutions, we must require that at minus infinity we have a zero result. Then the traveling wave solution is only one for each value of lambda. Here it is. And also the perturbed equation has only one, has only translations in X and T, and they are both interesting, but a lot of conservation laws, a lot. Not only momentum is conserved, but the resulting perturbed equation has a lot of conservation laws. One more interesting quality of this perturbed equation. If we start with some compact profile, then the result of decay is this very shock wave with oscillating tail, which moves to the right with very high speed. This is initial profile, and this is its deformation or decay at time 30 units. One more example of this, another initial profile. This time, the oscillating table is almost negligible. You can see it here. But it is negligible. This rather complex initial profile still becomes a shock wave. In this quality, these shock waves remind, are likes of shock waves for KdVB equation. First, their traveling wave solutions are also shock waves, and also compact initial profile decays to a shock wave with or without oscillating table moving in opposite direction. Now, for transformation of KdV that retain energy, the generating function for energy is given here, and quite in analogy of the case with momentum, one can obtain the perturbation of low order which retain whose adding retain energy. The formula is quite simple, and B is again an arbitrary function. If we take B equals just U, we obtain F such an and the transforming equation has this form. It also has some interesting qualities, characteristics. Well, it has solitons. The traveling wave for this equation are well familiar. Well, they're very much the same as for KDV itself, but it is they are shifted. Besides the KDV soliton, it also is shifted by 2a square. The original soliton is not shifted, and this one is not just the classical soliton. But it is not the whole story, because as you will see in the next two videos, the compact initial datum scatters in a number of solitary peaks of different height and velocity with constant such characteristic, and possibly an oscillating tail moving in the opposite direction, just as it becomes with compact initial data, for arbitrary compact initial data for KDV itself. Here are examples. The red profile is initial profile. You see the peak of constant form and velocity. One may think that it is a soliton, but it is not a soliton, because solitons are has such a form. And this one is not shifted, and it doesn't, so it is not a soliton in itself. The first idea is that now when this peak is isolated from the tail, this peak is some other soliton, but it is not so. But the behavior of one more example. Initial peak is somewhat lower, and then it scatters in at least 5 solitons. And this picture is in a KDV theory is called multi-solitons, and in KDV theory there is a very complex formulas describing this phenomenon. In this instance, there is no tail, at least at this period of time. Probably no, because the tail usually develops very, very quickly. the equation for triangle solutions is a rather simple one. Well, we'll just assume that U is U of x plus Vt, and this equation is integratable. Well, it is. I didn't write down the answer. It is possible, but the result is quite implicit. To obtain some explicit formulas, it is probably impossible. Well, I have to recall that, remind that multi-solitons of GDEq are not simple sum of separate solitons. They are given by complex formulas connected by complex analysis on algebraic manifolds. This straightforward method to obtain such moving solutions will probably has no perspective. Well, let us see another example in 3D 1 plus 2D equations of plasma. In low dimensions, there are only 3 conserved quantities, conservation laws. They are called in physical jargon energy. Well, it's of course energy, and this is cross helicity and magnetic potential. Here, F and phi are both arbitrary functions. Their generating functions in respective order are given here in this formula. Well, let us see transformation which retain something. Well, this F and G are functions of dependent variables and their derivatives. Of course, low order, because otherwise it is undescribable. First, we see for energy retaining transformation. In this case, the equation for exact form looks like that. Well, there are quite a lot of such transformation. There are different ways to obtain it. I have to get again to the very start. This is a scalar product, and if we obtain a scalar product equal to 0, we obtain a retaining addendum. We can simply put F equals to eta delta and J as nu U. That is this is I remind, this is generating functions for energy. If I take how to produce the orthogonal vector to this, well, change places first and from first to second line and put one minus in one case. You get simply orthogonal product which is which equal to 0, simply to 0. It is not even the exact form, but clean 0. And of course, you can find a lot of such deformations. Another method to obtain solutions here is not to decide this system as a whole, but think that this part is equal to this part and another addendum to another. No, very simple assumption. There are a lot of solutions to this system, and for instance, we can choose A and B in such a way and obtain the deformations of such a form that this deformation retain energy. For mean magnetic potential, mean magnetic potential is has such a generating function. So the equation for possible perturbation is like this. Since f is multiplied by 0, it is arbitrary function. And for 3, we have such an equation, and for instance, the solution of this equation is given here. And at the end, the cross-helicity. The cross-helicity, its generating function is vector from this is first component, this is another component, and equation is such. Well, what here is the cross helicity generating function. Well, no, there are some computations, and here is one of the possible solutions. There is a lot, it may be concluded, there is a lot of perturbation that retain this each certain conservation law. And it is easy to understand that for systems, not for simple equations, such a perturbation are numerous. Well, about conclusion. These nice pictures and videos which I demonstrated show that perturbed equations usually inherit not only the retained quantity, but some other algebraic property of transformed equations. Well, it is still another way to use selective decay as an instrument to qualitative approximation of for behavior of perturbed equation. Thank you for your attention.
Well, thanks a lot. Questions, remarks, comments? No comment, no remark, no question. Okay, then thanks a lot again. So we meet in a week, the same time, and again in Zoom. Have a nice week and a nice weekend. Goodbye.